Every year, the Indian banking sector loses hundreds of crores to intra-bank frauds, money laundering, and coordinated scam rings. The vast majority of these internal threats remain completely undetected by the existing security infrastructure. Most traditional banking security relies on SQL-based anomaly detection. This approach evaluates transactions as isolated statistical records stored in a tabular format, checking individual accounts for sudden deviations in typical behavior. Modern financial crime deliberately bypasses this individual account monitoring. Criminals distribute their anomalies across dozens of mule accounts, keeping individual transaction amounts small enough to stay below the statistical thresholds that trigger alerts. Tabular data becomes obsolete when analyzing networked crime. To expose these structures, investigators have to visualize the connections between the transactions. Catching modern fraud rings requires a system built to analyze structural relationships as its primary function, rather than relying on isolated numbers in a database. The objective is to build solutions targeting both internal and external banking threats. The proposed IKARIS solution operates as a comprehensive monitoring system. The IKARIS architecture is a security pipeline built on two main pillars: a graph-native intelligence engine for detecting external threats, backed by an immutable, permissioned blockchain to monitor internal threats. This diagram shows the architectural blueprint. It maps the flow of transaction data as it moves from raw input at the top, down through graph modeling, risk scoring, and finally into a tamper-proof audit trail. True systemic security requires exposing external criminal networks through relational graph data, while simultaneously using cryptography to prevent internal actors from manipulating those findings. Looking at the top blue tier of the data ingestion pipeline, we start with graph modeling. Here, the foundational data model abandons rows and columns. Instead, bank accounts are mapped as distinct nodes, and every financial transaction is mapped as a directed, weighted edge connecting those nodes. This relational map instantly exposes shell accounts used as intermediaries. You can visibly track money layering, where an account receives dozens of small deposits from disconnected sources before immediately funneling it out as a single consolidated sum. The engine deploys specific algorithms to automate this discovery. Cycle detection identifies funds looping back to a point of origin, while relational centrality measures locate the central hubs facilitating the most illicit traffic. A mathematically perfect layering chain often produces zero statistical red flags when you view each transaction in isolation. By utilizing graph modeling, invisible intermediaries and money laundering paths become obvious the moment the system draws the edges between them. This detail from the chain diagram highlights the second analytical layer, identifying distributed, coordinated networks. Coordinated fraud, like the operations seen in Jamtara, a district in India notorious for localized cybercrime networks, defeats single-node detection because criminals spread the anomalous behavior across too many separate accounts. To catch this distributed activity, the IKARIS system introduces a three-dimensional clustering heuristic that evaluates groups of accounts simultaneously. The first two dimensions enforce strict parameters on the transfers. The system looks for groups sending amounts with a similarity variance of plus or minus 2%, executed within tight temporal proximity to one another. The third dimension correlates these transfers with geographic co-location. The engine cross-references the origination data using postal PIN codes, bank branch locations, or IP subnets. When all three vectors align, the system generates a coordinated fraud score. This alignment isolates distributed statistical noise and translates it into a definitive structural fingerprint. Traditional fraud monitoring relies on vague alert thresholds that frequently trigger false positives, leading to severe alert fatigue for investigators. Returning to the pipeline funnel, the green tier focuses on how the system addresses that fatigue through anomaly detection. Moving down to the light green risk scoring tier, we can see how these anomalies are precisely quantified. The system generates a composite risk score using a transparent formula. It calculates weighted signals from graph centrality, transaction velocity, amount deviation, and geographic inconsistency. This mathematical engine then integrates with an active learning feedback loop, an automated process where the machine learning model adjusts its parameters based on new input. Every time an investigator renders a verdict on a flagged cluster, whether they confirm it as a true positive or dismiss it as a false positive, that decision feeds directly back into the model to continuously calibrate its precision. Because the formula is transparent, auditable, and self-correcting, it drastically reduces false positives over time, keeping the system operationally sustainable. The most critical vulnerability of any security system is the insider threat, where corrupt analysts can manipulate records or quietly dismiss valid warnings. The IKARIS architecture solves this through the component shown in this chain diagram, the permissioned blockchain audit layer. This implementation of blockchain technology is completely separated from financial payments. It operates purely as an internal, immutable audit infrastructure that is distributed across different bank departments. The system relies on cryptographic hashing. Every transaction, risk score, and investigator action is converted into a unique alphanumeric string and permanently recorded as a block. This acts as an automated failsafe. If an internal actor maliciously marks a legitimate money laundering cluster as a false positive, that exact action is immutably recorded in the chain and cannot be erased. By making these records cryptographically immutable, the system neutralizes the insider threat and secures the integrity of the entire investigative pipeline. Looking at the bottom orange tier of the data funnel, we reach the final output stage. The reporting phase integrates LLMs, or large language models. These are advanced AI systems trained on massive datasets to understand and generate text. Specifically, IKARIS utilizes models with 70 billion parameters, such as Llama or Quen. The LLM processes the complex graph metrics alongside the blockchain-verified risk scores to draft an analysis of the threat. The output is a standardized, human-readable document called a SAR, or Suspicious Activity Report. These are the official forms required by financial regulators. The system formats them automatically using Jinja 2, a Python templating engine that places the data into the exact required structure. By strictly grounding the LLM in verified transaction data, the system prevents AI hallucinations, producing accurate reports that safely accelerate the investigative workflow. The IKARIS architecture provides dual-layered institutional protection. The graph algorithms act outward to expose external criminal networks, while the blockchain audit layer turns inward to secure the bank's own personnel. Regulatory bodies like the RBI and Financial Intelligence Unit receive complete, cryptographically verified evidence packages that speed up subsequent legal proceedings. The implementation of graph-native intelligence and blockchain auditing shifts financial fraud defense away from reacting to isolated statistical anomalies, moving it toward a proactive analysis of the entire network topology.